Sorry for starting a minute late today. Sorry we're starting late. We had that nationwide competition that a couple of people in this room participated in. It was a challenging test, and if you're interested in seeing this test, if you didn't get a chance to take it earlier today, then I will have copies available after spring break. So we start on page 28, and before we do, we'll take our look at the calendar. Today we talk about this new idea, something called a function. Can you guys give me a sense? Raise your hand if you feel comfortable with this idea of f of x. F of x. Somewhat have seen it before, maybe a little bit. Yep. So that's what we talk about today, and I think that that's what we talk about for quite a long time after today. So if you take a look at all of these things right here, you see the word function appearing a bunch of times, okay? So here's our introduction to that word function, and as you can see, it's going to carry us through for a while. One other thing about the calendar, what is happening Friday? Quiz number 5 on the last 3 classes, including today, okay? All right. Okay, so let's go ahead and take a look at page 28. Now, in looking over the notes that I printed out for you guys, I think that there's probably too much stuff in this section. So we're going to kind of skip around. I don't want to rush through stuff, so we're going to skip so we don't have to rush. We're going to start with, can we start with Matt with number 3? Let's say that sentence one more time. Okay, that is a function. It takes in something, it spits out something. That's all that it does. For example, you could have a function that takes in a number and spits out double the number. It takes in a number and it spits out double the number. For example, if it takes in 3, what does it spit out? 6. It takes in a number, it spits out double the number. Somebody else, if it takes in -4, what does it spit out? -8. Just take in something, doubles it, and gives you the answer. That's what a function is. Take something in, gives you something out. Now, there's an important subtlety here in this definition. It says each input has one and only one output. Is that true in this case? Like if I say it takes in 5, if you double 5, what do you get? 10. Is there any way to get anything other than 10 when you double 5? No, which is okay because that's what's supposed to happen. We're supposed to, if I say 5, everybody in the world is supposed to say 10. We can't have some people saying 10 and somebody else saying 15. It wouldn't be a function anymore. Right? Okay, so Matt is bringing up a good point here. So what if we had something like that? And if I tell you that I'm thinking of x equals 9, and y is supposed to be the answer to that equation up at the top. So what's the answer to the bottom equation here? Y equals? Aren't there 2 different answers to the bottom equation? So the input here was 9, and the output was either 3 or -3. Is that a function? It's not. That breaks the fundamental rule. Each input is supposed to have one and only one output. If I say I'm inputting 9, and somebody says 3 and somebody else says -3 and they're both right, it means we're not looking at a function. That's a good observation. Okay, so let's go down to this birthday.
It's a function of y. There's only one x value for y value.
That's right. Yeah, so we're going to look at some pictures and we'll talk about this thing that Iris is picturing towards the end of class today. Thank you. Yeah, we'll see it. We'll see that today. Thank you. Can we go to this birthday thing for Eric? Birthday function 1. Okay, so let's just share some names. Okay, so the input here, first input is Sam. Sam, what's your birthday? Okay, fair enough. Hazen? November the 12th. And Megan? Megan, do you have an H in your name? October the 16th. Okay, so the question is this a function? for each of these people, we had an input. The input was the person. The output was their birthday. Is there any way I could ask Sam, again, what his birthday is, and he'll give me a different answer besides February 7th? Are you really? Sam, you're ruining my function example here. So in theory, Sam has one and only one birthday, which makes this a function. Given the input of Sam, there is only one answer for what his birthday is. It's February the, where'd it go? It's February the, we lost some stuff here. Look at, there it goes. Okay. So given an input of a person, their birthday is unique. They have only one birthday, so they will never give two different answers. So that is a function. And let's go to Iris for birthday function 2. No, just tell us the, just read that for us. That's nice and loud. Can you just read, just read that. Okay, so let's think about what this function is that Iris is saying is not a function. So the input is a month and a day, and the output is a person born on that day. What was your birthday?
1/365th of the entire population was born on any given day.
Maybe.
Approximately.
Maybe. What's your birthday? October 19. October 19. Input is October 19. What's an output? Anybody know this guy's name? Anybody know his name? Nobody knows his name? I have failed you guys. Could you share with everybody what your name is, please? That is Taylor. Okay, so input is a date, output is somebody born on that day. Is it possible that we could put an October 19th and have some other name appearing here? Yeah, okay, not likely in this room. Anybody else born October 19th in this room? No. Somebody, Megan was actually kind of close, right? Only 3 days apart, your birthdays. But certainly somewhere in the world, and in fact somewhere probably within 100 feet of us, we could find somebody whose birthday is October 19th. So I'll just put other person over here, which makes this thing not a function. Given an input, October 19th, there could be more than one output, more than one person born on that day. So first one is a function, yes. Second one, no. We have decided, yes? Yeah, so then we're, yeah.
So you can't rule out the possibility there could be
yeah.
Not that likely, but it's possible.
Right. So yes, we could limit stuff, in which case we could make this thing a function just in our local view here, but my definition is not a function. Okay, so speaking about birthdays and stuff, are we surprised that we had 2 people that were only 3 days apart? There's only, how many of us are there? 4, 8, 12, we have 15 people in this room. Are we surprised they're only 3 days apart? No. Let's see if anybody's even closer in the room. Let's just see. Raise your hand if you were born in January. February. Anybody born in February? Okay, Sam was born in February. Anybody born in March? On what day? Perfect. April. 19th, 25th, and 12th. Okay. May. June. July. August. Go ahead. On what day? Great. September. Yes? Okay, September 17th, so it's another 3 days apart. What did we say, 3rd and 30th? October? Okay, yes. Okay, so we actually have a 14 in October 16 and October 19. So 3 people within over the same week their birthday was. Any Novembers? Okay, we said it already, but go ahead. Good, and December. Okay, so it turns out you can actually, people are surprised by how close birthdays are with not that many people. If I were to say how many people do you need in a room so that there's a 50-50 chance that 2 of them have the same birthday, the answer is 23. If you're in a room with 22 other people, there is a 50-50 shot that 2 people in that room have the same birthday. We had only 15 people in here. We have less of a chance, but If we were to just get in a room with 22 people, there's a 50-50 chance that 2 of them have the same birthday. If you're in a room with 55 people, there's a 99% chance that 2 people in that room have the same birthday. It's really low.
If you have more than 365, the odds are 100%.
Also true. Okay, we'll go to the next page. Number 5, Megan. Okay, so the example we said out loud before was a function that takes in a number and doubles the number. That's the output. Here's the cubing function. All right, so this thing right here is read f of 2. Please don't read it as f times 2. It does not mean f times 2, and you will be forever confused if you look at it as an f times 2. You might even fall down. You're so shocked when you hear somebody say f times 2. So this is f of 2, and you could also say the value of f at 2, and it means you apply the rule to the number 2. The rule in this case is cube the number. How much is 2 cubed? 8. So then here's a very compact way to write that down. F of 2, meaning 2 cubed, which is 8. Nothing more, nothing less. That is a cubing function. Okay, next example. F of 3 is 3 cubed, or 27. F of negative 2 is negative 2 cubed, which is negative 8. Okay, and then we have this idea of inputs and outputs, right? Input whatever number you want. The output is the thing cubed. And so in general, this formula, the rule, the function is f of x equals x cubed. And that's going to be really important. So let me ask the question again. Raise your hand if you've kind of seen function stuff before, like that. Okay, so it looks like a lot more of us now that we've seen what I'm talking about. So this is maybe the most important idea for today, is that if you have a function, it looks like f of x equals blah. It means you take whatever's in the parentheses, in this case it's called x, and you change all of the x's over there to whatever's in the parentheses. So if I wanted to know what f of 7 was, according to this rule, you change all the x's to 7. And so it's 7 cubed. I should know 7 cubed. Is that 343? That can't be right. Could it be right? Maybe it's right. Is that right? Okay. All right, can you guys try number 6 with your table? Do we agree f of 4 is 64? F of 5 is negative 125? Okay, f of r I've left blank. What is f of r? It's r cubed. Let's see, we went somewhere. Okay, f of r is r cubed because the idea is you take whatever's in the parentheses and you change all of the x's on the right-hand side to what's in the parentheses. So that x cubed became r cubed. Now it's really tricky. X plus 2. I change all of the x's on the right-hand side to x plus 2. So what does it become? X plus 2 cubed. Nothing more and nothing less. We can expand it. We could expand it, but that's not the idea for this. Like, we are trying to introduce functions. This is the important thing here. So whatever's in the parentheses, you put it over here and you cube it. What was in the parentheses got put over there and got cubed. Do we see the pattern? That last one is a really strange thing because I told you what f of x was up at the top, and then I asked you to find f of something with x, and it's very weird to like define something in terms of the thing it's defined as, right? Like the x is appearing in the definition, but then we're using the x plus 2 instead of the x. It's quite strange. It almost seems circular. But the idea is just to naively replace all of the x's with whatever's in the parentheses. Do that and you will not go wrong. Some folks, I want to just give credit where credit is due, actually multiplied all this out. So can somebody tell me what did we get? Okay, I'm going to put this part in parentheses. That is not my goal for today. The goal is the first part. All right, let's see, so we already said f of x does not mean f times x. Don't read it that way. Let's go to 7, and I think we're up to Hazen. Okay, so real common to use those letters, just like X and Y are the most common letters for variables. F, G, and H are the most common letters for functions. We're going to come back to 8 after we do some stuff on the next page. So we'll go to Sam for number 9.
So the following function using for representations let F be Fahrenheit temperature plus Celsius.
Okay, let's pause there. Does anybody know the relationship between degrees Fahrenheit and degrees Celsius? If you have a Celsius temperature, do you know how to find the corresponding Fahrenheit temperature? All right, there's a 32 in there. Okay, so all right, so Ben says find the Fahrenheit equivalent of a Celsius temperature. You multiply the Celsius temperature by how much? 1.8, and then add 32. Okay, this rule is the correct rule. For me, 9/5 is what I've got in my head instead of 1.8, but they're the same. Did you guys know this? I mean, like Ben knows it. You got the right formula. This is how you go between Celsius and Fahrenheit. Multiply by 1.8, add 32. Now subtract 32, which is what Michael had said is part of the formula going the other direction. Yeah. Okay, so that's the verbal rule. It's just kind of written out in English with very few mathematical symbols, just a couple of numbers. Then we're going to represent that same thing with a, well, let's actually do this first part here. It says find the Fahrenheit equivalent of 10 degrees Celsius. Can you guys use that formula, the English formula, and figure out if you have 10 degrees Celsius, what is your temperature in Fahrenheit? I got 50. You guys got 50? 50 what? 50 degrees Fahrenheit. That's right. If it's 10 degrees Celsius, it's 50 degrees Fahrenheit. Which one is colder? 10 degrees Celsius or 50 degrees Fahrenheit? They're the same. I can't fool you guys. I see some smirks on your faces. Come on, Ian. They're the same. They're either both cold or both hot, or whatever you think they are. But 10 degrees Celsius means 50 degrees Fahrenheit. Okay, the algebraic rule. Here's where we take the English that Ben gave us and we translate it into symbols. So f of c equals, so he said multiply Celsius by 1.8. What letter should we use for Celsius? C. So you do C times 1.8. I'm going to go ahead and put the 1.8 in the front. And after you've multiplied by 1.8, what do? You add 32. Any questions about that translation? Okay, let's use the algebraic rule to find f of 10. You guys have the formula right there. Find f of 10. What do we get? We get the same, and we did the same thing before, right? We just did it from English. Now we did it from a formula. Of course, it's the same. But this example is supposed to show us that oftentimes with functions, there's more than one way to represent them. So Ben gave us the way in English, then we translated it into a formula called an algebraic rule. Turns out there's two other real common ways to represent functions. One of them is down here in part C. This is called the numerical way, which is just a table of values. So the first column is the inputs, the degrees Celsius. The second column is the output, degrees Fahrenheit. Using the table, can you find the Fahrenheit equivalent of 10 degrees Celsius? How much is it? It's 50. Do you see it in that row right there? Input 10 degrees Celsius, output is 50 degrees Fahrenheit. There's something appealing about the table. If I just wanted to know what the Fahrenheit equivalent of 30 degrees Celsius is, would you rather use the rule or use the table? Table, it's right there. If you use the rule, you have to do work. So there are some upsides to the table. What's the downside to the table? What's that? Okay, we don't know what the formula is. Other downsides to this table? It doesn't show everything. If I want 30, then super, the table is easy. But if I want 31, the table isn't worth anything, right? So the formula is much more general. You can take anything you want, plug it into the formula. Okay, somebody took a few different numbers and plugged it into the formula and came up with the table. Pros and cons. And the last way is the graphical way, where you look at a picture. And here's the graph of, I'm just going to write it in our standard looking thing, y equals 1.8x plus 32. If I asked you to graph that, you'd buy that it could look something like this, right? You've graphed a lot of lines. What is the 32? That's the y-intercept. Do you see it? Right, there's your 32 right over there. What's the 1.8? That's the slope. You go over 1, you go up 1.8, over 1, up 1.8. It's, that's what it is. But it's not really those letters, so let's tell it like it is. It was really f equals 1.8c plus 32. And you can see that the c is down there where normally there's what letter? X. And then there's f. Normally there's a y, but it's okay. It's the same thing. All right, can you guys use the graph to find the Fahrenheit equivalent of 10 degrees Celsius? I already know the answer is 50 because it's been 53 times. But can you find the answer looking at just the graph? So where do I go first if I want to find the answer? I find 10 on the Celsius axis, the x-axis. So there's 10, and then we go up until we hit the line, and then you got to find the y. And what is the y? 50. Good. Joe, you don't like it? You believe it? Joe is pointing out one of the fundamental weaknesses of the graph, is that it's just an approximation. I can't even be confident that I found the point that goes with 10, right? I could have found 10.2 or 9.8. So that's one of the weaknesses of the graph. One of the strengths of the graph is that as long as you're okay with this idea of being close enough, then you have a lot more info than is in the table, right? In fact, you see these 6 points right here are exactly those 6 dots on the graph. See the dots that are kind of highlighted? So how did you get the graph? Well, you could just plot a few of these. You don't even need 6. You could just do 2 and then connect the dots. So the table is, it's got some pros and cons. It's got the con that it's approximation stuff. It's got a pro that it's got a lot more info than is in the table. And for me, my purpose is I'd like you to be comfortable doing whatever you can with all 4 of these different methods. 4 different ways we've talked about to represent a function. That thing that we skipped is down here. I think we're going back to Surge for number 8 on the previous page. It's on the bottom of the, yeah. Okay, so those are the 4 things. We saw each of those 4 for our Fahrenheit example. Any questions about the different representations for functions? Okay, let's go to Joe for number 11. Have we used these words this semester? Domain and range? I think this is, did we use domain? We said domain is the things that are allowed to go in for the x's. Yeah, so this is the same as what we had said before, just domain is the inputs, range is the outputs. Let's take a look at 12, Ben. Okay, so Ben is at least not saying f times x, so I appreciate that. He is saying f parentheses x. I would like him to say a shorter word than parentheses, of. So we will say f of x, okay? All right, so domain and range. Domain is the inputs. The inputs are the x's. Looking at this graph, if you go over here to like -5, is there a graph somewhere above or somewhere below -5? Is there any part of this funny looking shape with the ears here? There's nothing above or below -5, right? What that means is if I asked you to plug -5 into this function, there's no answer. I mean, there's nothing out there. And it's because -5 is not part of the domain. It's not allowed because there's no picture there. Where does the picture start? It starts at -4. And then from -4, you can find a dot. And from -3, you can find a dot. And from all these things, you can find a dot. And it's even okay if you have to go down to find the dot. Where's the last dot? Is it 7? So the domain for this function is all the x's between -4 and 7. Graph starts at -4 on the far left and continues until we get to 7 at the far right. Domain is x's. The range is y's. So we're looking not left, right anymore, but bottom to top. Where does this graph start at the bottom? It starts at -2. That's the lowest point on the graph. And then it goes up and up and up, and we get all of these points until we get to what number at the top? 6. 6 is the highest number you will get. And so the range for this function is all the y's between -2 and 6. Questions on that? Okay, so let's try part B. We're supposed to find f of a lot of this stuff. So I'll do one of them and then you guys can try the rest in your groups. F of -3. Is that -3 an x or a y? It's an x. F of x. The thing inside the parentheses is almost always called x. So you go to x equals -3. It's right here. You look up if you need to. You look down if you need to. You look wherever you can find the graph. In this case, the graph is up. And once I found the graph, what do I head towards? We got to go to the y-axis. You're trying to find the y value that corresponds to x equals -3. What does it look like here? Looks like 4. F of -3 is 4. You find the x, then you find the curve or the line, then you find the y. Can you guys try the rest of B as well as C and D? Lots of chatter with your neighbors. All right, let's just get some answers up here. How much is f of -1? Is 5. F of 0? Also 5. Is that a problem? I thought we said for a function, for any input, there can be only one output. But didn't we just get 2 different 5s? Is that a problem?
Yeah.
We said for a single input, there better be only one output. For the single input of 0, what was the output? It's 5. For a different input of -1, well, the output is 5, but that's okay. The function just says for a single input, you better have only one output. It is perfectly legal to have 2 different outputs that are, like 2 5s sitting on the output. That's fine. F of 4 is how much? Also 5. F of 5 is 6. Okay, then we go the other direction. Remember we had said the number in the parentheses is almost always what letter? It's the x. Those things in the parentheses are the x. How about all these numbers in red that you gave me? What letter are those? Those are the y's. So if you ever see like a f of something equals, you're looking at a y value. So in this very next line, it says f of x equals 2. It's your job to know that that's a y that I'm talking about. If I'm talking about an x, I'm going to put it in the parentheses. If it's out here, it's the y. So you find y equals 2, and what's the answer? Looks like it's around 6. So x equals 6. And then again, this number out here is the y. So if I wanted to equal 3, well, it turns out that there's actually 2 different answers here. So it looks like -4, and then we just had to estimate over there. What did we come up with? 5.8, something like that. Okay, any questions on that? All right, let's go to 13, and I think we're back to Tyler. Okay, so again, the domain is the inputs. Inputs are usually X. What letter is the input in this case? It's T. You can always find the input letter by looking in the parentheses. That's the input. And so the domain that we're interested in is all the allowable T values. What are the allowable T values for this example? It's anything from 0 to 4. That's what that is saying. It's saying here's a function, only exists between 0 and 4. If you try to plug in something outside of 0 to 4, we get mad and start throwing heavy stuff on the roof. These jokes aren't going to be funny in the video because nobody's going to, like, what was he talking about? Okay, so the domain here is just all the stuff between 0 and 4. Normally, just looking at this function, it's perfectly legal to plug in t equals 5. Nothing bad happens by plugging in t equals 5. But for some reason, the person that gave us this function decided the only parts that we were interested in was 0 to 4. Maybe this is like a production, you know, like you're making like little toys and you can't make any more than 4. So there's no point in allowing us to plug in 5. For whatever reason, it's okay. Here's another example. We'll go to Michael. Oh, can you do B? Okay, so again, the domain is the inputs, which is the x's. What are the only x's that we're allowed to plug into this function? This function is only good between 1970 and 2000. Maybe after 2000, it's a different function. But you can only plug in stuff from 1970 to 2000 because that's what the person told us. All right, let's try going to 14, Katrina. Go ahead. Okay, so let's think about this function right here. Square root of x minus 2. There's no explicit domain. They didn't say only plug in x's from this to this. So we have to think about what x's make sense. And I think that we have talked about domain in this context before, like way back. Did we not look at examples like this? What's the danger when you're trying to take square roots? Can't be negative under there, right? Don't take the square root of a negative number. So we have to work really hard to make sure that we're not taking the square root of a negative. Okay, to say negative or positive, 0 is the cutoff. And if I don't want it to be negative, then what symbol goes in here? Is that right? Not negative. That's what we're trying to avoid. Okay, bigger than 0 is not negative. Equal to 0 is not negative. So that's right. So we solve for x by adding 2. And we get x is greater than or equal to 2. And that's the domain. So all the x is bigger than or equal to 2. So sometimes it's not given to you explicitly, but you have to like really think about making sure that you don't plug in anything that's illegal, right? And so this is called an implied domain. You have to think about what values of x you're allowed to plug in. Okay, we're going to skip B and jump down to 15. And 15 will go to Iris. Can you just read 15 out loud? Okay, so let's take a look at the picture. F of -2. Is that -2 the x or the y? It's the x in the parentheses. So we find -2, we go up, we find the y-axis, and how much is f of -2? That's 5. It was 5 before, it's still 5. F of 4 is where things go a little funny. We go to the x equals 4, it's right there. What's the problem? It's going to have 2 different answers. You choose to go up, and what do you get for f of 4? Okay, so on the one hand, f of 4 is 5, but maybe some of us choose to go down. And what's the answer down there? So f of 4 is 5 on the one hand, or f of 4 is -1 on the other hand. That's a problem, because we said for a function, for a single input, there had better be one and only one output. What was the single input here? 4. For that input of 4, what were the 2 outputs? 5 and -1. So is that a function over there? No. Not a function. For an input of 4, we have 2 different outputs. Okay, and this is actually the thing that Iris was talking about earlier in the class. She talked about vertical lines and things kind of crossing back on itself. And how can you tell geometrically that something is going to go wrong? Well, the problem here was that there was a green vertical line that hit the graph how many times? How many times did that green line hit the graph? Hit it twice, which is a problem, right? How many times did this vertical red line hit the graph? Only once. That was okay. But you know that there are problems if you can draw a vertical line that hits the graph more than once. All right, we'll go to Eric for 16. Okay, can you say that one more time? Okay, thank you. Matt, 17. Okay, can you guys write yes or no? Is it a function for each of these? And check with your neighbors. Okay, what do we say about the first one? Is it a function? Yes. Second one? Yes. Third one? No, because we can draw a vertical line that hits the graph more than once. Fourth one? No, we can draw a vertical line that hits the graph more than once. Fifth one? Fifth one is where it gets a little bit sticky. How many times does that vertical line hit the graph? Once. That one, that one, that one. How many times did they all hit the graph? Just once. But the question is, can you find a single vertical line that hits the graph twice? And in this case, you can. That single line right there hits 2 filled in dots, 2 dots that are on the graph. If a single line hits twice, it is not a function. So is this one a function? No. It just barely fails to be a function. It was like so close to being a function, but just that single green line makes it not a function. But we'll end on a positive here. Is this last one a function? Yes, because we have removed that problem. That vertical line appears to hit the graph twice, but that dot down there at the bottom is open, which means it's not really there. It's just our symbolic way of saying the graph stops just short of hitting this dot. So that last one is a function. Questions on that? Okay, so here is the plan. We have 22 minutes. I don't know exactly how long it's going to take to do the group thing. Let's see how far you guys can get in 10 minutes, and then we will come back together, okay? Go through that group thing and we'll reconvene. Okay, and the reason that we're moving on to the next section, we have about 10 minutes left. We have what at the start of class next time? We have a quiz. And I can also tell you that Friday's class has a lot of stuff in it, coupled with the time that we're going to take on the quiz. I want to make sure we don't run out of time. So we're just going to grab these 10 minutes that we have right now. Okay, so we'll go to number 1, and I forget who our reader is. Matt, did you go again? Go ahead, Matt. Number 1, the paragraph adapted. Okay, so I've given you very little information, but we're just looking for like some almost pure guesses. How fast is the current? Nope. The current is 5 miles an hour, and Fred is swimming against that current. And how far does Fred need to swim? 10 miles. Can you guys make a guess in your tables? Spend 30 seconds debating and just come up with a speed that you think might minimize the amount of energy that Fred has to spend on the whole 10-mile trip. 30 seconds. Random, almost random guesses. What table has a guess? What do you guys say? All right, one table says 10 miles per hour, and it wasn't just a guess, they had a method. Well, how did you come up with 10? They said twice the speed of the current. Let's go twice the speed of the current. That, like, at least it has some appeal. It's not a random number. It's like maybe that's just what you're supposed to do, is go twice the speed of the current. Do you guys have a guess? All right. This is the problem, is that one group can then sway the rest of the groups. Go ahead. In the corner here, what do you guys say? Not sure. Of course you're not sure. I haven't told you anything. How about back here? We have a guess. What is it? 5.1. Are you guys playing the Price is Right? What are you doing? Okay, let's think about the possibilities here. Suppose that that Fred were to swim, I don't know how fast a fish can swim, 20 miles an hour. He's really cruising. What's the good news with making this trip at a really high speed, like 20 miles per hour? It's a short trip, right? He's going to get there quick. What's the downside? He's using a lot of energy during the whole, like every moment of this short trip. It is tough for Fred to swim 20 miles an hour, even for a short period of time. On the other extreme, what if Fred were to swim at 5.1 miles an hour? So it's kind of like a reasonable pace. So he's not going to be tired at any moment because he can swim 5.1 miles, no problem. What's the downside? It's going to take a long time because the current is taking away 5 of those miles. So he's really effectively only going 0.1 miles an hour. That trip is going to take 100 hours for poor Fred. So there's this kind of balancing act. And in fact, if you guys end up taking a calculus course, you'll see this come up a bunch, where it's this balance. Like it's really bad to go quick, and it's really bad to go slow, and somewhere in the middle, not necessarily right in the middle, is like a happy medium, like some balancing point, which is the best. Okay, let's go to number 2. Sam. E of V. Okay, so there's the formula. What's the input? V. Given a velocity, what's the output? Is energy. given a velocity, that formula will tell me how much energy Fred is going to use, how many calories he will burn making this trip. Okay, can you guys use your calculators and split up the work? See if you can fill in all those numbers in the table with that formula. Okay, so let's come on back together. And I just want to highlight that anytime you have this kind of like really annoying type repeated calculation that you have to do, there is a shortcut using the calculator. We know how to type stuff into y equals. I typed in my formula, the 6.5 v cubed, except I don't have v. What do I have to use? X. You just have to use x. So I've typed that in, careful with the parentheses. And then I went into my table and I just typed in my numbers on the table. And so my table has exactly the numbers that I'm interested in. I guess I missed 5. I'll put 5 in here too. Wait, is that right? Oh yeah, it started at 6. Yeah, it's good. So those are the numbers from the table, and that's a quick way to get it. And so that's fine. So I'll just put that there and get rid of this guy. Okay, and then let's take a look at part B, Hazen. Okay, so we've kind of started to do this using the calculator up here. Which letter is X? Is V. So I'm going to call that an X. And instead of E, we have a Y. All right, so get rid of that guy, we'll get rid of that guy. So we have X and we have Y. And if we want to graph that function, we need to rewrite it in terms of X and Y. So instead of E of V, what letter is that whole thing? That's the Y. Equals, and then instead of V, we have X's. So this is exactly what I typed in, and exactly what you guys are going to type in right now. So see if you can get your calculator to look like that. Okay, and once we've got the thing typed in, we want to really think carefully about the window. What's the smallest X in the table that I've created? Even smaller than 6 in the table? Isn't 5.1 in the table? So how about we say 5? And doesn't 5 make sense as the slowest Fred might go? Because if he goes exactly 5, what happens? He will stay stationary, right? He won't make any progress at all. So it doesn't make sense to have him go backwards, like less than 5. And the fastest speed in my table is 15. How about we go to 20? And then as far as the Y's go, again, the Y's are the energy levels. What was the smallest energy level in my table? It was like 1100 something. Maybe it gets under that. I don't know. In fact, I actually like seeing my x-axis. I'm going to go from 0. And what's the highest energy I saw? It was 8600. I'll go to like 10,000 or something. Oopsies. 0 and then 10,000. And so if you pick that window and you take your time thinking about the window, and you hit graph, you'll actually see something. I think hopefully we'll see something kind of nice. So we'll pick up here next time, but again, what's the horizontal? What's going on the x-axis? Those are the velocities. So here are all the different velocities I might choose. And what's the vertical axis? Is the energy. And so you can see if you're going like 5.1, you're using a lot of energy. Then you go a little bit faster. Here I'm at like 6 miles an hour, 7 miles an hour. It looks like it kind of bottoms out somewhere in here, someplace. But then if you take too long, if you go too fast, if you go way to the right, you're going really quick. Turns out you start using more and more energy. So what we're after, and what a lot of calculus is after, is finding that bottom point. So we will get there on Friday. Yeah.
This is a weird
dimension.
I will fix that. Okay, we'll see you guys on Friday.